Terraform is one of the most popular DevOps tools for infrastructure as code. In this course, Vigen will walk you through the fundamentals of Terraform and help you not only understand the basics, but also practice and gain hands-on experience. If you're visiting our channel for the first time, don't forget to subscribe as we upload new videos and courses all the time.
Let's start with how application delivery works in a traditional infrastructure model and how it evolved with the emergence of technologies such as cloud computing and infrastructure as code. Let's go back in time and look at how infrastructure was provisioned in the traditional IT model. Let us consider an organization that wants to roll out a new application. The business comes up with the requirements for the application. The business analyst then gathers the needs from the business, analyzes it, and converts it into a set of high-level technical requirements. This is then passed on to a solution architect. The solution architect then designs the architecture to be followed for the deployment of this application. This would typically include the infrastructure considerations such as the type, spec, and count of servers that are needed, such as those for front-end web servers, back-end servers, databases, load balancers, etc. Following the traditional infrastructure model, these would have to be deployed in the organization's on-premise environment, which would mean making use of the assets in the data center. If additional hardware is needed, they would have to be ordered via the procurement team. This team will put in a new hardware request with the vendors. It can then take anywhere between a few days to weeks or even months for the hardware to be purchased and delivered to the data center. Once received at the data center, the field engineers would be in charge of rack and stack of the equipment. The system administrators perform initial configurations, and the network administrators make the systems available on the network. The storage admins assign storage to the servers, and the backup admins configure backups. And finally, once the systems have been set up as per the standards, they can then be handed over to the application teams to deploy their applications. This deployment model, which is still quite commonly used today, has quite a few disadvantages. The turnover time can range between weeks to months, and that's just to get the systems in a ready state to begin the application deployment. This includes the time it takes for the system to be initially procured and then handed over between teams. Also, scaling up or scaling down the infrastructure on demand cannot be achieved quickly. The overall cost to deploy and maintain this model is generally quite high. While some aspects of the infrastructure provisioning process can be automated, several steps such as the rack and stack, cabling, and other deployment procedures are manual and slow. With so many teams working on so many different tasks, chances of human error are high, and this results in inconsistent environments. Another major disadvantage of using this model is the underutilization of the compute resources. The infrastructure sizing activity is generally carried out well in advance, and the servers are sized considering the peak utilization. The inability to scale up or down easily means that most of these resources would not be used during off-peak hours. In the past decade or so, organizations have been moving to virtualization and cloud platforms to take advantages of services provided by major cloud providers such as Amazon AWS, Microsoft Azure, Google Cloud Platform, etc. By moving to cloud, the time to spin up the infrastructure and the time to market for applications are significantly reduced. This is because with cloud, you do not have to invest in or manage the actual hardware assets that you normally would in case of a traditional infrastructure model. The data center, the hardware assets, and the services are managed by the cloud provider. A virtual machine can be spun up in a cloud environment in a matter of minutes, and the time to market is reduced from several months, as in the case of a traditional infrastructure, to weeks in a cloud environment. And infrastructure costs are reduced when compared with the additional data center management and human resources cost. Cloud infrastructure comes with support for APIs, and that opens up a whole new world of opportunity for automation. And finally, the built-in auto-scaling and elastic functionality of cloud infrastructure reduces resource wastage. With virtualization and cloud, you could now provision infrastructure with a few clicks. While this approach is certainly faster and more efficient when compared to the traditional deployment methods, using the management console for resource provisioning is not always the ideal solution. It is okay to have this approach when we are dealing with limited number of resources, but in a large organization with elastic and highly scalable cloud environment with immutable infrastructure, this approach is not feasible. Once provisioned, the systems still have to go through different teams with a lot of process overhead that increases the delivery time. And the chances of human error are still at large, resulting in inconsistent environments. So different organizations started solving these challenges within themselves by developing their own scripts and tools. While some use simple shell scripts, others use programming languages such as Python, Ruby, Perl, or PowerShell. Everyone was solving the same problems, trying to automate infrastructure provisioning to deploy environments faster and in a consistent fashion by leveraging the API functionalities of the various cloud environments. These evolved into a set of tools that came to be known as infrastructure as code. Let's now talk about Terraform and go over some of its features at a high level. Terraform is a popular IAC tool which is specifically useful as an infrastructure provisioning tool. Terraform is a free and open source tool which is developed by HashiCorp. It installs as a single binary which can be set up very quickly, allowing us to build, manage, and destroy infrastructure in a matter of minutes. One of the biggest advantages of Terraform is its ability to deploy infrastructure across multiple platforms, including private and public cloud, such as on-premise vSphere cluster or cloud solutions such as AWS, GCP, or Azure, to name a few. These are just a few of the many resources that Terraform can manage. So, how does Terraform manage infrastructure on so many different kinds of platforms? This is achieved through providers. A provider helps Terraform manage third-party platforms through their API. Providers enable Terraform manage cloud platforms like AWS, GCP, or Azure, as we have just seen, as well as network infrastructure like BigIP, Cloudflare, DNS, Palo Alto Networks, and Infoblox, as well as monitoring and data management tools like Datadog, Grafana, Auth0, Wavefront, and Sumo Logic. Databases like InfluxDB, MongoDB, MySQL, PostgreSQL, and version control systems like GitHub, Bitbucket, or GitLab. Terraform supports hundreds of such providers and as a result can work with almost every infrastructure platform. Terraform uses HCL, which stands for HashiCorp Configuration Language, which is a simple declarative language to define the infrastructure resources to be provisioned as blocks of code. All infrastructure resources can be defined within configuration files that has a .tf file extension. The configuration syntax is easy to read and write and pick up for a beginner. This sample code is used to provision a new EC2 instance on the AWS cloud. This code is declarative and can be maintained in a version control system, allowing it to be distributed to other teams. So we said that the code is declarative, but what does declarative mean? The code we define is the state that we want our infrastructure to be in. That's the desired state. And this on the right is the current state, where there's nothing. Terraform will take care of what is required to go from the current state to the desired state without us having to worry about how to get there. So, how does Terraform do that? Terraform works in three phases: init, plan, and apply. During the init phase, Terraform initializes the project and identifies the providers to be used for the target environment. During the plan phase, Terraform drafts a plan to get to the target state. And then, in the apply phase, Terraform makes the necessary changes required on the target environment to bring it to the desired state. If for some reason the environment was to shift from the desired state, then a subsequent Terraform apply will bring it back to the desired state by only fixing the missing component. Every object that Terraform manages is called a resource. A resource can be a compute instance, a database server in the cloud, or in a physical server on-premise that Terraform manages. Terraform manages the lifecycle of resources from its provisioning to configuration to decommissioning. Terraform records the state of the infrastructure as it is seen in the real world, and based on this, it can determine what actions to take when updating resources for a particular platform. Terraform can ensure that the entire infrastructure is always in the defined state at all times. The state is a blueprint of the infrastructure deployed by Terraform. Terraform can read attributes of existing infrastructure components by configuring data sources. This can later be used for configuring other resources within Terraform. Terraform can also import other resources outside of Terraform that were either created manually or by the means of other IAC tools and bring it under its control so that it can manage those resources going forward. Terraform Cloud and Terraform Enterprise provide additional features that allow simplified collaboration between teams managing infrastructure, improved security, and a centralized UI to manage Terraform deployments. All these features make Terraform an excellent enterprise-grade infrastructure provisioning tool. Well, that was a quick introduction to Terraform at a high level. In this section, we will learn how to install Terraform. Terraform can be downloaded as a single binary or an executable file from the Terraform download section in www.terraform.io. Installing Terraform is as simple as downloading this file and copying it to the system path. Once installed, we can check the version by running the command terraform version. The latest version of Terraform as of this recording is 0.13, and we'll be making use of this version throughout the course. Terraform is supported on Windows, Mac, and several other Linux-based distributions. Please note that all the examples and labs used in this course will make use of Terraform running on a Linux machine and specifically the version 0.13. And that's it. We can now start deploying resources using Terraform. As stated earlier, Terraform uses configuration files which are written in HCL to deploy infrastructure resources. These files have a .tf extension and can be created using any text editor such as Notepad or Notepad++ for Windows, or command line text editors such as Vim or Emac in Linux, or it could be any IDE of your choice. So, what is a resource? A resource is an object that Terraform manages. It could be a file on a local host, or it could be a virtual machine on the cloud such as an EC2 instance, or it could be services like S3 buckets, ECS, DynamoDB tables, IAM users or IAM groups, roles, policies, etc. Or it could be resources on major cloud providers such as the Compute and App Engine from GCP, databases on Azure, Azure Active Directory, etc. There are literally hundreds of resources that can be provisioned across most of the cloud and on-premise infrastructure using Terraform. We will look into some of these examples later in this course, but for the first few sections, we will stick to two very easy to understand resources: the local file type of resource and a special kind of resource called a random pet. It is important to use a simple resource type to really understand the basics of Terraform, such as the lifecycle of resources, the HCL format, etc. Once we gain a good understanding of the basics, we can easily apply that knowledge to other real-life use cases, and we will see that in later sections of this course. In this lecture, let's take a look at providers in more detail. After we write a Terraform configuration file, the first thing to do is to initialize the directory with the terraform init command. When we run terraform init within a directory containing the configuration files, Terraform downloads and installs plugins for the providers used within the configuration. These can be plugins for cloud providers such as AWS, GCP, Azure, or something as simple as the local provider that we use to create a local file type resource. Terraform uses a plugin-based architecture to work with hundreds of such infrastructure platforms. Terraform providers are distributed by HashiCorp and are publicly available in the Terraform registry at the URL registry.terraform.io. There are three tiers of providers. The first one is the official provider. These are owned and maintained by HashiCorp and include the major cloud providers such as AWS, GCP, and Azure. The local provider that we have used so far is also an official provider. The second type of provider is a verified provider. A verified provider is owned and maintained by a third-party technology company that has gone through a partner provider process with HashiCorp. Some of the examples are the big IP provider from FI Networks, Heroku, DigitalOcean, etc. And finally, we have the community providers that are published and maintained by individual contributors of the HashiCorp community. The Terraform init command, when run, shows the version of the plugin that is being installed. In this case, we can see that the plugin name HashiCorp/local with the version 2.0.0 has been installed in the directory. The Terraform init is a safe command, and it can be run as many times as needed without impacting the actual infrastructure that is deployed. The plugins are downloaded into a hidden directory called .terraform/plugins in the working directory containing the configuration files. In our example, the working directory is /root/terraform-local-file. The plugin name that you see here, HashiCorp/local, is also known as the source address. This is an identifier that is used by Terraform to locate and download the plugin from the registry. Let's take a closer look at the format of the name. The first part of the name, which in this case is HashiCorp, is the organizational namespace. This is followed by the type, which is the name of the provider, such as local. Other examples of providers are AWS, Azure RM, Google, Random, etc. The plugin name can also optionally have a hostname in front. The hostname is the name of the registry where the plugin is located. If omitted, it defaults to registry.terraform.io, which is HashiCorp's public registry. Given the fact that the local provider is stored in the public Terraform registry within the HashiCorp namespace, the source address for it can be represented as registry.terraform.io/HashiCorp/local, or simply by HashiCorp/local by omitting the hostname. By default, Terraform installs the latest version of the provider. Provider plugins, especially the official ones, are constantly updated with newer versions. This is done to bring in new functionality or to add in bug fixes. And these can introduce breaking changes to your code. We can lock down our configuration files to make use of a specific provider version as well. We will see how to do that later in this course. Let us now take a look at some commands available in Terraform. The first command we will take a look at is the Terraform validate command. Once we write our configuration file, it's not necessary to run Terraform plan or apply to check if the syntax used is correct. Instead, we can make use of the Terraform validate command like this. And if everything is correct with the file, we should see a successful validation message like this. If there's an error in the configuration file, the validate command will show you the line in the file that is causing the error with the hints to fix it. In this example, we have used an incorrect argument for the local file resource. It should be file permission and not file permissions. The next command that we are going to see is the Terraform fmt or the Terraform format command. This command scans the configuration files in the current working directory and formats the code into a canonical format. This is a useful command to improve the readability of the Terraform configuration file. When we run this command, the files that are changed in the configuration directory is displayed on the screen. The Terraform show command prints out the current state of the infrastructure as seen by Terraform. In this example, we have already created the local file resource, and when we run the show command, it displays the current state of the resource, including all the attributes created by Terraform for that resource, such as the file name, file and directory permissions, content, and ID of the resource. Additionally, we can make use of the -JSON flag to print the contents in an JSON format. To see a list of all providers used in the configuration directory, use the Terraform Providers command. You can also make use of the mirror subcommand to copy provider plugins needed for the current configuration to another directory, like this. This command will mirror the provider configuration in a new path /root/terraform/new_local_file. We saw how to use Terraform output variables in one of the previous lectures. If you want to print all output variables in the configuration directory, use the command Terraform output. You can also print the value of a specific variable by appending the name of the variable to the end of the output command, like this. The Terraform refresh command is used to sync Terraform with the real-world infrastructure. For example, if there are any changes made to a resource created by Terraform outside its control, such as a manual update, the Terraform refresh command will pick it up and update the state file. This reconciliation is useful to determine what action to take during the next apply. This command will not modify any infrastructure resource, but it will modify the state file. As we saw earlier, Terraform refresh is also run automatically by commands such as Terraform plan and Terraform apply. And this is done prior to Terraform generating an execution plan. This can, however, be bypassed by using the -refresh = false option with the commands. The Terraform graph command is used to create a visual representation of the dependencies in a Terraform configuration or an execution plan. In this example, the local file in our main.tf file has a dependency on the random pet resource. This command can be run as soon as you have the configuration file ready, even before you have initialized the configuration directory with Terraform in it. Upon running the Terraform graph command, you should see an output like this. This text generated is hard to comprehend as it is, but it is a graph generated in a format called dot. To make more sense of this graph, we can pass it through a graph visualization software such as GraphViz. And we can install it in Ubuntu using apt, like this. Once installed, we can pass the output of the Terraform graph to the dot command, which we installed using the GraphViz package, and generate a graphic like this. We can now open this file via a browser and it should show a dependency graph like this. The root is the configuration directory where the configuration for this graph is located. We can see that there are two resources, the local file called pet and the random pet resource called mypet that makes use of the local and the random provider respectively. And finally, we can see that the local file called pet depends on the random pet resource called mypet, as we have used a reference expression in the local file resource that points to the ID of the random pet. Well, that's all for now. At KodeKloud, we have multiple learning paths curated just for you to help you to go from a beginner to an expert in various DevOps technologies. So don't forget to check it out. And don't forget to subscribe to this channel as we publish more courses very often.